Welcome to another episode of Learning. Please like my videos and share them with your friends and colleagues. Please join as a member in my channel and support me and my channel. Please subscribe my channel if you have not already subscribed. Thank you. Right. We continue the discussion of the solutions of the problems that have appeared in the CSIR National Eligibility Test held in the month of March 2025. This is a rescheduled examination for Assam Center. In this video, we discuss the solution of a problem from the section Complex Analysis, and it is related to the Cauchy's inequality, and the same thing is related to the generalized Liouville's theorem also. This question is placed in part C, which is a multiple select question. There may be more than one answer, and it carries 4.75 marks. The question ID is 706559. Further, this question is suitable for all these examinations. Right. The given question is, let f be a non-zero holomorphic function defined from the non-zero complex numbers to the set of complex numbers such that modulus of fz is less than or equal to mod z to the power of 5 by 2 plus 1 by mod z to the power of 1 by 2 for all z belongs to the set of non-zero complex numbers. Which of the following statements are true? We are given 4 statements. Option 1, f has a pole at z is equal to 0. Option 2, there is an entire function g such that f is equal to g on the set of non-zero complex numbers. Option 3, f is a polynomial of degree at most 2. Option 4, f has an essential singularity at z is equal to 0. Right. We now discuss the solution of the problem in detail. We are given f is a non-zero analytic function from non-zero complex numbers to the set of complex numbers satisfying this inequality. Mod fz less than or equal to mod z to the power of 5 by 2 plus 1 by mod z to the power of 1 by 2 for all z belongs to the set of non-zero complex numbers. Agreed. Now, we want to study the nature of the singularity z is equal to 0. You can obviously see here z is equal to 0 is a singularity. What type of singularity it is? We are given 2 options. Option 1, f has a pole z is equal to 0. Is it a pole? Option 4, f has an essential singularity at z is equal to 0. Is it an essential singularity? That's what we want to study. Now take the inequality and multiply throughout by mod z. Then it will be mod of z times fz less than or equal to mod z into mod z to the power of 5 by 2. That is mod z to the power of 7 by 2 plus mod z into 1 by mod z to the power of 1 by 2 is mod z to the power of 1 by 2. Let us take the limit z tends to 0. Limit z tends to 0 of the left hand side. Mod z of z is less than or equal to limit z tends to 0 of the right hand side. That is mod z to the power of 7 by 2 plus mod z to the power of 1 by 2 in brackets. And you know 7 by 2 is positive Positive 1 by 2 is positive. Limit z tends to 0. Mod z to the power of 7 by 2 is 0. So also mod z to the power of 1 by 2. 0 plus 0, that is equal to 0. From this, that means limit z tends to 0. Mod of z of z is 0. Is less than or equal to 0. From this, it follows limit z tends to 0 of z of z is equal to 0. That means limit z tends to 0 of z minus 0 into the function f of z is a finite quantity. That is a finite number. That means z is equal to 0 is a removable singularity of the function f. When it is a removable singularity of the function f, we overrule options 1 and 4. It cannot be a pole, it cannot be an essential singularity. Therefore, options 1 and 4 are not true. Agreed. Agreed. We move to the next slide. Right. Option 2. There is an entire function g such that f is equal to g on the set of non-zero complex numbers. What is that we have proved? Just now we have proved, we have shown that z is equal to 0 is a removable singularity of f. So we redefine the function f and such that it becomes analytic or holomorphic at z is equal to 0, and thereby f can be extended to an entire function. Let's call that as the g. Since z is equal to 0 is a removable singularity, we define f of 0 in such a way that the function becomes analytic or holomorphic at z is equal to 0, and thereby it becomes an entire function. So that a new entire function is the extended function of f. So this extended function, let's call it as g of z, is an entire function, right? And g of z is equal to f of z for all z belongs to c minus the singleton 0. That means the restriction of g is f on c minus 0, c minus the singleton 0. So that's what is that we have proved. There is an entire function g such that f of g is equal to f is equal to g on c minus singleton 0. So the option 2 is true. Good. So we are left with only one option. That is option 3. Right. F is a polynomial of degree at most 2. Right. Now we have an entire function g of z, and it satisfies mod of g of z is less than or equal to mod of z to the power of 5 by 2 plus 1 by mod of z to the power of half, z not equal to 0, because the restriction of g on c minus 0 is f, wherein f satisfies this one. Right. So we want to find the nature of g of z. Let us consider an arbitrarily chosen circle C, that is mod z is equal to r, that is a circle with center 0 and a radius capital R. Is an arbitrarily chosen one. Clearly, g of z is an entire function analytic everywhere on the whole of the complex plane. So g of z is analytic inside and on C, that is mod z is equal to R, and what happens to this inequality on mod z is equal to R? Then mod of gz is less than or equal to mod z, that is r to the power of 5 by 2 plus 1 by r to the power of 1 by 2. Let's call this r to the power of 5 by 2 plus 1 by r to the power of 1 by 2 as m say. And this is true for all z on C. Yes. Yes. So we recall the conditions of the Cauchy inequality, wherein it is analytic inside and on C, mod z is equal to R, and mod of gz is less than or equal to capital M for all z on C. So all the conditions of Cauchy inequality are satisfied. Therefore, by Cauchy inequality, mod of the nth derivative of g at 0 is less than or equal to capital M into n factorial by r power n is equal to 1, 2, so on and so forth, where m is r to the power of 5 by 2 plus 1 by r to the power of 1 by 2. Agreed. Now, g of z is an entire function, and it is analytic even at z is equal to 0. So we can write down its Taylor's expansion about z is equal to 0. And this is the Taylor's expansion. G of z is equal to sigma n is equal to 0 to infinity a n into z to the power of n, where a n is the nth derivative of g at 0 by n factorial. Now, modulus of a n is equal to modulus of a n is g nth derivative of g at 0 by n factorial. That is 1 by n factorial into modulus of the nth derivative of g at 0. And the nth derivative of g at 0 is less than or equal to m into n factorial by r power n. Yes, true for all n is equal to 1, 2, so on and so forth. Now, n factorial cancels. For m, we write down r to the power of 5 by 2 plus 1 by r to the power of 1 by 2 into 1 by r to the power of n. Multiply. Then r to the power of 5 by 2 into 1 by r to the power of n is 1 by r to the power of n minus 5 by 2 plus the second one is 1 by r to the power of n plus 1 by 2. Now let us take as r tends to infinity. Is it possible? Yes, because f of g of z is an entire function. R can be made as big as possible. Right. Now as r tends to infinity, yes, you can do it because g of z is an entire function. Then modulus of a n will, as r tends to infinity, this will become 0. The second one also becomes 0. Yeah, the first one will become 0 provided n is greater than 5 by 2. Yes, mod of a n tends to 0 when n is greater than 5 by 2. This means a n is equal to 0 for n greater than 5 by 2 means n greater than 2.5. That is n is equal to 3, 4, so on and so forth. So what will be our g of z? That is the expansion. So that thus g of z is equal to a0 plus a1z plus a2z square. That's all. The remaining a_n's are all 0. What is this? It's a polynomial of degree at most 2. When g of z is a polynomial of degree at most 2, so also f. So f is a polynomial of degree at most 2. True. Thus option 3 is true. Summarizing all the options, the answer to this question is options 2 and 3. That is the detailed discussion of the solution of this problem. Yeah, this option 3 I will show you by using generalized I'll show you using. So we'll take 3. F is a polynomial of degree at most 2. I will show you by using generalized Liouville's theorem. Generalized Liouville's theorem. So we have an entire function g of z and it satisfies mod gz is less than or equal to mod z to the power of 5 by 2 plus 1 by mod z to the power of 1 by 2, z not equal to 0. Right. We want to find the nature of g of z. For mod z greater than 1, it means you can make z as big as possible, mod z as big as possible. We have for mod z greater than or equal to 1, 1 by mod z to the power of 1 by 2 is less than or equal to 1. Yes. And this is less than or equal to mod z to the power of 5 by 2. Yes, because mod z is greater than 1. So this above inequality now becomes mod of gz is less than or equal to mod z to the power of 5 by 2 plus 1 by mod z to the power of 1 by 2 is also less than or equal to mod z to the power of 5 by 2. So we'll get 2 times of mod z to the power of 5 by 2 for mod z greater than 1. Right. Now we have an entire function g of z that satisfies mod of g of z is less than or equal to 2 times of mod z to the power of 5 by 2 for all mod z greater than or equal to 1. We recall generalized Liouville's theorem. This states if an entire function g of z satisfies modulus of gz is less than or equal to m times of mod z to the power of k. In our case m is 2, k is 5 by 2. For some constants m greater than 0, k greater than or equal to 0. And for sufficiently large mod z, so mod z greater than 1, we can make it mod z sufficiently large. Then g of z must be a polynomial of degree at most the floor function of k. Floor function of k, that is the greatest integer less than or equal to k. That is also the greatest integer function. So you can see this result in a book entitled Complex Variables with Applications by Ponnuswamy and Herb Silverman at page 266. Now, by generalized Liouville's theorem, g of z must be a polynomial of degree at most, floor of k. What is our k? M is 2, k is 5 by 2. Floor of 5 by 2, floor of 2.5. The largest, the greatest integer less than or equal to 2.5. That is 2. That is 2. So that means g of z is a polynomial. Since f of g of z is a polynomial of degree, at most 2. Since f is equal to 0, for z not equal to 0, f is a polynomial of degree at most 2. Thus, option 3 is true. It's a very beautiful application of generalized Liouville's theorem. And in the last slide, I have shown you another beautiful application of Cauchy's inequality. I make a remark, to prove generalized Liouville's theorem, we use Cauchy's inequality. But anyway, this will be interesting, I have shown you. And summarizing all the options, the answer to this question is options 2 and 3. That is the detailed discussion of the solution of the problem from complex analysis, which uses Cauchy's inequality and generalized Liouville's theorem. Right. And for me, this is a very, very good application of two great results. Right. I am sure that you have understood the solution of this problem. Thank you for watching this video now. Please like my videos and share them with your friends and colleagues. I make an appeal to all of you. Please join as a member in my channel and support me and my channel. Please subscribe my channel if you have not already subscribed. Yes, I am sure we are going to meet you, all of you, in another episode of learning. Enjoy learning mathematics. I wish you all the best. Thank you.